Good morning or good evening, wherever you are in the world. It is a great pleasure and an honor for me to be able to present our exciting recent work on a more secure and more efficient future internet at this virtual USENIX Security Symposium. I would like to thank my collaborators Tobias, Marc, Christoph, and Adrian who made this work possible. During the next 10 minutes, I will explain to you what the data plane does in a path-aware internet and highlight the main insights of our work. I would like to start, though, with the idea of how a perfect internet might look like. Imagine, if you can, an internet in which source address spoofing is no longer possible because every router in the network can perform source authentication. Imagine an internet in which there are no more route hijacks, which occur on a daily basis today due to misconfigurations or attacks, because there is a secure routing process. Imagine that end hosts are not bound to use a single path determined by the network, but can select a path that suits their needs of latency, bandwidth, or other criteria, path control. And finally, imagine that end hosts can actually verify that the network followed their choices using path validation. The maybe surprising but great news is that such an internet exists already today. It is called SCION, and it has been developed over the past decade by numerous researchers over the world. Today, it is mature enough that it is in production use by several entities in sectors like finance and government, and several ISPs offer native SCION connections to their customers. Similar to other internet architectures, SCION consists of two core components: a control plane which discovers the network topology and distributes paths, which in SCION is secured by cryptographic signatures, and a data plane where data traffic is being forwarded at high speeds, such that asymmetric cryptography is not efficient enough and symmetric cryptography is used. The core difference between SCION and the current IP-based internet is that SCION is path-aware, so end hosts can exercise control over the paths their packets take. Also, there are extensions like OPT that provide source authentication or path validation in addition. Let me focus on some challenges that path-aware internet architectures face. As I just said, end hosts can actually choose the paths that are taken by their packets. But the internet consists of numerous independent networks called autonomous systems that have preferences and policies of their own. So the challenge in a path-aware architecture is how can these autonomous systems restrict the selection available to end hosts such that their own criteria are enforced as well. For example, consider this abstract network topology where each node represents an autonomous system. A, B, and C might be quite happy to forward packets along this path that goes directly from A over B to C. However, this path is certainly not desirable. It contains a loop and it probably violates a number of policies of the on-path autonomous systems. Path authorization is then the property that end hosts are restricted to use previously authorized paths by autonomous systems. SCION uses cryptographic tokens to achieve this property, and similar network architectures do the same. This is based on the observation that in today's hardware, cryptographic operations are highly efficient and can be even several times faster than memory lookups. For example, the AES block cipher can be computed on commodity CPUs within around 10 nanoseconds. So SCION computes these cryptographic tokens in its control plane. Let's consider again this example of a path between A, B, and C. These autonomous systems exchange signed routing messages, and in these messages collect path information. Each autonomous system adds its local routing information, which essentially consists of the links that connect them to their neighbors. And they add a cryptographic token in the form of a message authentication code that protects this information. In fact, this is slightly simplified. In SCION, this cryptographic token also takes into account the neighbor's information. Now, the big benefit here is that in the data plane, where this local routing information is available in the packet header, it can be directly used to determine where to forward packets. This removes the need for the huge routing and forwarding tables that are needed in today's internet, and the need of longest prefix matching in the IP-based internet. Instead, this cryptographic token is checked, and routers simply forward the packet according to this local routing information. Now, there is an issue here, which is that this approach suffers from an inherent trade-off between overhead and security. For every hop of the path, such a cryptographic token is needed, which can, for longer paths, create substantial overhead. One might be tempted, therefore, to simply reduce the size of these tokens, but each token individually must be long enough to withstand sophisticated attacks. The core issue here is that even if the probability of forging a token is relatively small, if an attacker manages to do that, it can be reused for sending many additional packets. And this brings us to the core insight and contribution of this paper. EPIC makes the observation that for autonomous systems, individual forged packets are generally not a threat. Path authorization protects economic interests of ASs, but there, a single packet that traverses an unauthorized link is not really an issue. So instead of using static tokens that are used, for example, by SCION, EPIC uses longer keys that are subsequently used to compute short per packet max that cannot be reused to send additional packets. An attacker may still have a small chance of forging a MAC and create a packet that traverses an unauthorized link, but this is limited to a single packet and cannot be reused to send additional packets. In addition, there is a longer unforgeable MAC for the destination, which can filter the few packets that might escape autonomous systems on the way. By leveraging recently proposed schemes for efficiently deriving symmetric keys, EPIC also provides source authentication and path validation in a more efficient way than previous systems like OPT and icing. So the main message that I want you to take home is that EPIC enables path authorization for autonomous systems, source authentications for all routers, and path validations for the endpoints, while only having small computation storage and communication overhead. We evaluated this communication overhead of EPIC and compared it to previously proposed systems, where EPIC performs very well. For both variants of EPIC that we propose, the overhead is lower than in comparable systems, and it is very low for currently typical path lengths in the internet. We also created a proof of concept implementation of EPIC in Intel's data plane development kit and evaluated its performance. This graph here shows the forwarding performance of an EPIC router in gigabits per second, and we can see that even on commodity hardware with a low number of computing cores, a 40 gigabit link can be easily saturated. Also, EPIC is parallelizable, so the throughput can be scaled up almost arbitrarily by simply adding more computing cores or additional hardware. This brings me to my conclusion. EPIC solves multiple challenges that are faced by path-aware internet architectures. It strengthens path authorization by preventing the reuse of forged packets. It provides source authentication and path validation, and it does this with no per flow or per source state in routers, with low communication overhead and low computational overhead, where only a few block cipher operations are necessary. So overall, EPIC is efficient enough that in the internet, every packet can be checked at the network layer. I hope this short presentation sparked your interest and a lot of questions. Please check out our paper and get in touch with me either during the conference or send an email to one of my collaborators or me. Thank you very much.